All right, so we've made it to the fourth chapter in this course, and what we're going to talk about here is something that you've all learned in your probably the first chemistry course you ever took. You learned in general chemistry about valence shell electron pair repulsion theory, or as a lot of people call it, VSEPR or VSEPR, right? And so what is this? Just to remind you, this is a theory to predict the structure of molecules. This essentially comes from octet theory, and it's just kind of a derivative of octet theory for the most part. This is a completely empirical theory, right? What does that mean? That means it's it doesn't have any underlying basis. It's just kind of looking for patterns and trying to come up with rules that fit within those patterns, okay? And so as such, it's not backed up by quantum mechanics. There's no quantum mechanical underpinning for VSEPR. Despite this, VSEPR works very well. Most of the time, in fact, VSEPR does a very good job at predicting the kind of baseline structures of a molecule. And it's really simple and easy to use, which is why it's so popular, right? So it's an incredibly useful theory. I'm not questioning that. But what you will see throughout this chapter is, and later on in chapter 5, is that it has some severe down pitfalls. Some of the conclusions that you would logically come to based upon a VSEPR structure turn out to just be false through a wide range of other experiments and quantum mechanical based theories. All right, so hopefully you know how to do VSEPR structures, but we're going to go over it and I'm going to teach it to you perhaps in a different way than you've learned before. The basis of VSEPR is that electron pairs can be bonding or non-bonding. Non-bonding electrons are called lone pairs. And I'm going to define something that I call the steric number. And so this is the number of ligands plus the number of lone pairs. And actually, when I teach general chemistry, I also teach it this way too, because it seems to be easier for students to comprehend this way. So steric number is number of ligands and number of lone pairs around a central atom, right? We're always going to be talking about a central atom. For species with an odd number of electrons, so you have some sort of radical, the single unpaired electron acts similarly to a lone pair. And one of the central kind of tenets is that non-bonding and bonding electrons want to maximize their distances from one another due to electron-electron repulsion. So electrons want to maximize their distance from one another. And that will sort of dictate the overall geometry of a molecule. And so there's various steric geometries. You've probably learned up to 6, perhaps you've gone further, but these are the idealized bond angles. You might remember, and we'll talk about this, that the bond angles will deviate from these. They'll be less than these numbers. This is what VSEPR predicts if you have lone pairs. But you go down and you go from linear, trigonal planar, tetrahedral, trigonal bipyramidal, octahedral. Those are steric geometries 2 to 6. And then 7 is pentagonal bipyramid. So this is good exercise for you is to think about the point groups of all of these different baseline geometries, VSEPR geometries. But for pentagonal bipyramid, this is point group D5H when everything's symmetric. You have the same ligands. Y, you basically have a pentagon in the equatorial position, and then you have 2 axial ligands there. And then there's a square antiprism for coordination, a steric number of 8. You can have, higher steric numbers. Those become increasingly rare. But there are some inorganic complexes that, have higher coordination numbers of, for example, 10 or 11. Okay, so really the key here is all about counting electrons, and specifically what we care about are valence electrons. which is normally all we care about when we're talking about bonding. So you're going to first determine the number of valence electrons on the central atom. So look at a periodic table. Boron is in group 3, right? So it's going to have 3 valence electrons. Carbon's in group 4, etc. And then you're going to add 1 to that number if the molecule has an overall charge of -1, or subtract 1 if the molecule has an overall charge of +1, etc. So you have to accommodate for the overall charge of the molecule. And then you're going to subtract 1 for each ligand that needs 1 electron to complete its valence shell. And so there's various ways to think about this. Here are some examples of these so-called 1-electron ligands. Hydrogen, any halogen like fluorine, OH, CH3. And the way to think about this is, do you have a 1 electron, something that needs to subtract 1 electron? Think about if HX is a stable molecule, whatever the ligand is in question. So if it's H, it's going to be HH, that's H2, that's stable, right? Your intuition, chemical intuition, hopefully tells you that H2 is a stable molecule. H with a halogen, HF, HCl, HBr, all those are stable. HOH, that's water, of course. HCH3, that's methane. And so that's one quick way to tell if your ligand falls into this category. You're going to then subtract 2 for each ligand that needs 2 electrons to complete its valence shell. So this would be something like just an oxygen atom by itself, a terminal oxygen atom. Why? Because if you added 2 hydrogens to that, that would get you H2O, right? Water. So that's a stable molecule. Or you're going to subtract 3 if the ligand needs 3 electrons. So that would be like terminal nitrogen. Again, if you add 3 hydrogens to it, that's going to give you H3N or NH3 ammonia. That's stable. And the last thing you're going to do is you're going to divide the remainder by 2 to find the number of lone pairs. And so if the molecule has an odd number of electrons, the extra 1/2 after dividing by 2 corresponds to an unpaired electron. And so you're going to want to round up to find the appropriate steric geometry on this slide. Okay, so that's basically the rules that you need to know in order to draw out the baseline VSEPR structures. Fairly simple, no quantum mechanics underpinnings here like we started with chapter 3. And the reason for that is because there aren't any quantum mechanics underpinnings. Okay, so in the next video, we'll do several examples, help you gain practice on this.